Okay, so in this problem we have a bicyclist who's traveling to the right and she suddenly brakes. And in one situation she brakes with only the rear wheel, and in another situation she only brakes with the front wheel. And based on this problem we're asked to comment on possible differences between rear and front wheel braking as viewed from a dynamics perspective. So I'm going to start this problem by actually drawing a free body diagram of the young lady, and if I do that we'll note that we have some mg here at the rider. We'll have some normal force with ground on the rear wheel, which I'll call NR. We'll have some normal force here on the front wheel, which I'll call NF. And we have at least the perspective of having front wheel braking and rear wheel braking, which I'll call FR and FF respectively. Now I'm going to draw them both at this instant, and I can draw conclusions by essentially setting one of these two equal to 0. So if I do this, now that I've got my free body diagram, I can go ahead and apply my kinetics equations, and I'm going to do so assuming classical XY notation. And so I'm going to start by summing forces in the x direction here and setting that equal to the mass of the individual times the acceleration of g in the x. And if I do this, I'm going to have minus ff minus fr is equal to m times agx. And we can call this equation 1. I can also sum forces in the y direction for this individual, and here's hoping that they have 0 acceleration in the y direction. And so if I do this, I'll have nr plus nf is minus mg is equal to 0, and we can call this equation 2. I can also sum moments about the center of mass of the rider, and if I do this, I'll hopefully again we'll have 0 angular acceleration for this rider. And so if I do this, I'll have one force creating a positive moment, that'll be nf, and its moment arm will be bf. And I'll have 3 forces creating negative moments, so I'll have minus nr times br, minus fr times d, and minus ff times d, and that has to equal 0, and we can call this equation 3. Now at this juncture we have two different scenarios that are possible, and so in scenario 1, what we're going to have here is that we'll assume that it's rear wheel braking, so I'll have fr is equal to, in this case, mu k times nr, and we'll have ff is equal to 0. So this will be our first scenario. So if I go ahead and reduce these equations under this assumption, I'm going to have minus mu k times nr is going to equal m times agx. I'll also have from equation 2, nr plus nf minus m is going to equal mg. And from equation 3, I'll have that nf times bf minus nr times br minus mu k times nr times d is equal to 0. So I can work through these equations and find agx. So if I do that, I'm going to start by saying that nf is going to equal mg minus nr. And if I substitute that into the moment equation here, I'm going to have that mg times bf minus nr times bf minus nr times bf, times br minus mu k times nr times d is going to equal 0. What's this mean? Well, I get here that nr is then equal to, if I move everything onto the other side, I'll have m times g times bf divided by, in this case, bf plus br plus mu k times d. And if I plug that into agx, that means I'm going to get agx is equal to minus mu k times mg times bf divided by m times quantity bf plus br plus mu k times d. So if I work this out, mass is going to cancel, so I'll have minus mu k times g times bf divided by quantity bf plus br plus mu k times d. Now I can also look at scenario 2, and in scenario 2, I'll have here that fr is equal to 0, and I'll have now that ff is equal to mu k times NF. So if I work this out, I'm going to have minus mu k times NF is equal to m times AGX. I'm going to have, again, NR plus NF is equal to mg. And I'll have now NF times BF minus NR times BR minus mu k times NF times D is equal to 0. I'm going to substitute these equations or simplify these equations much like I did before. So let me create a little space for writing here. So if I do that, again from the middle equation now, I'm going to want to eliminate NR, so I'm going to have NR is equal to mg minus NF. If I plug that into the moment equation, I'm going to have NF times BF minus mg times BR, minus a minus is going to be plus NF times BR, minus mu k times NF times D is going to equal 0, which of course means that NF is going to equal mg times BR divided by, in this case, BF plus BR minus mu k times D. I can then plug that into the acceleration equation, and that's going to give me that AGX is equal to minus mu k times mg times BR divided by m times quantity BF plus BR minus mu k times D. Let me make sure I didn't make a typo up here up above. And that looks okay. And down here below, that looks okay. This is going to move to the other side. One moment here. Plus. Okay, I think everything looks okay there. Let me just check one more thing. Indeed, we seem to be okay. So now we can compare the two accelerations. I'll note that the masses cancel. So I'll have minus mu k times g times br divided by bf plus br minus mu k times d. Now we can compare these two quantities from front wheel braking and rear wheel braking. So this quantity here that's at the top of the page is the acceleration I get with front wheel braking. This is what we get with rear wheel braking. And we can compare, and depending on the exact setup that we have in our bike, you can see that you can get very different behaviors in terms of stopping. Interestingly enough, if you look at the normal forces, in addition to just looking at AGX, not surprisingly, you get a difference as well. Typically speaking, to be safest, I would normally go ahead and brake with that rear wheel. There's a tendency there, of course, is not so much to flip over, which is a darn good thing. Alright, I think this is a good place to stop, so I'll simply bid you adieu and urge you to plug in some numbers here and see what might drop out. Take care, everyone.